instructions.
Hi guys, so I think we're going to be starting our live stream today. We're going to be going through the arrow pushing for glycolysis. This lecture is going to serve both as our live stream and also as our lecture. Before we get started, can we ask everybody to mute themselves? Those of you working on Microsoft Word, I think it's time to show off your mics, or I'm going to take your power away. Mute all. All right, I've just muted everybody. So I will unmute you at the end, or allow you to unmute here. But we're going to go ahead and get going. If you have a question, please go ahead and ask it in the chat section. Carly is here and monitoring, so if you do have any questions, ask her there. Okay, so without further ado, some of our learning objectives for today. Oops, I need to turn on my screen sharing here. Let's see, can I share my screen? Okay. Screen sharing, start broadcast. Okay, here we go. So today we're going to be working on our arrow pushing mechanisms for glycolysis. So the last lecture that we all had together, I want to remind you that we worked on a number of mechanisms. First off, as everybody should remember, we had 3 rules that we covered. One was that acid-base reactions happen quickly. 2 is that bonds beta to carbonyl are labile, and 3 is because resonance. And then using those principles, we went over a number of different kinds of reactions, including ketoenol tautomerization, acid-base reactions, additional elimination, aldyl cleavage, and shift base. So you now should be pretty familiar with those overall concepts, and we're going to go and see if you can take what you've learned from that section to predict the reactions of glycolysis. Carly has reminded everyone, thank you, that I have posted this skeleton that I'm working on D2L, so you can download it and work along, and we'll also be posting the final reaction mechanisms when you're done. But let's go ahead and get started. So this is the very first reaction that occurs in glycolysis, the hexokinase reaction. And so everybody should be able to recognize this structure here. And the chat, what is that structure? What is that molecule? Glucose. Thank you, Brandon. You're correct. And so the very first priming reaction that happens in glycolysis is that we add a phosphate onto the 6th position of this molecule, as you recall, and we make this glucose 6-phosphate, right? And in order to do that, we have to do some chemistry with ATP. So does anyone want to guess how this reaction proceeds? Guesses from the chat? What's the first step? Hello? Ring opening. That is not true. So let me show you the first step here. So ring opening is what you're thinking of in the PFK or in the aldolase reaction. Yes, so we have everybody is right there with nucleophilic attack. So this is an additional elimination reaction. Now, if we wanted to go through each of the steps of this additional elimination reaction, we can. So this proceeds along the ways that we had shown before, where we have a nucleophilic attack of the hydroxyl here, right there on that phosphate group. And then from there, these electrons resonate. And then you go through this intermediate step right here. And then at this point, these electrons can resonate back. And at that time, these guys can leave and pick up a proton, regenerating this structure here plus ADP. Ooh, let's see if I can write that. Oops, cancel. See if I can write that in a somewhat ADP. Just looks like that. So that's the full mechanism. As we mentioned in the last class, this is an additional elimination reaction. this happens in 2 steps. Additional elimination reactions can be simplified to be just shown like this, where you have nucleophilic attack on a phosphate, and that can go just picking up a proton directly, and then that leaves ADP as a leaving group, and then you end up with this molecule here, glucose 6-phosphate. So one of those things that we practiced there quite a few times, the very first reaction mechanism, additional elimination, and that's how we form glucose 6-phosphate, the very first step that commits glucose inside the cell for glycolysis. Does that make sense to everybody? Oh, we have some questions here. Go ahead.
Why is the bond between the O and ADP not broken?
Why is the bond between O and ADP not broken? Well, that's connected directly to a phosphate. So if you're talking about why is this bond not broken? Is that the question there? The answer to that is that it has a filled valence shell, so we can't leave that bond on. Something has to go away. Does that answer your question? Good. Sounds like yes, it does. Any other questions on that? Is that clear? Okay, it looks like the class gets that one. So we're going to move on here to our next reaction. So this is the reaction that we talked about a little bit before, and the chat was right on this one, that this guy proceeds with a ring opening reaction to start. Okay, does anyone want to take a stab at how that ring opening reaction, how that proceeds? What's the very first step there? Base abstraction, that's correct. You abstract a proton of what, though? So let me give you some options here. Whoops, that's not an option. Yes, so a hydroxyl, we have options of 1, 2, 3, 4. So 4, 4, 4, 4. All of you who said 4 are correct. There we go. So that's exactly right. So, stop that. The base abstracts that proton right there. That leaves these electrons to move to there. These guys then open up and pick up a proton. Does that make sense? Then you have an open chain form of glucose. This guy right here. This actually happens very quickly and will happen at a very low rate spontaneously, and then it recloses spontaneously. But of course, naturally in an enzyme, this is catalyzed so that it happens quickly. So then the next step in order to get down here to the closed ring form is we have to undergo a ketoenol tautomerization reaction. Does anybody recall, so looking at this structure here, this structure right here, what is the most acidic proton that you see? Let me give you some options. We have 1, 2, there's a proton here, 3, 4, 5, or 6. Guesses? Yes, everybody is correct. 2. And why 2? What's the rationale? Why is number 2 the most acidic proton? Beta-carbonyl. Look at this class. Woohoo! Learning has occurred. That's great. So yes, that's exactly right. This guy is very acidic. He's very happy to come right off. And that's because he's beta-carbonyl. And at this point, this should be fairly intuitive that that the reaction proceeds just like that, and you end up with this nice ketone form right here. So that's the ketoenol tautomerization reaction. Okay, now that we've gotten there, tell me, how do you progress from there? How do you end up with putting the hydroxyl or the carbonyl in the number 2 position? Oh, good, because of resonance. So what? How do you proceed there? How do we get the ketone in the number 2 position? What needs to happen next in order to move from there? Base abstraction. Very good. So we need to abstract a proton, and then we have again options 1, 2, 3, 4, 5, 6. Which bond? 3. Good. Chat's right. Okay, and so the base abstracts this proton here. Whoop. And from that abstraction, these guys go out, pick up a proton, and you nicely open it up. And now you have the ketone in carbon 2. Now, for those of you guys who have watched my lecture on glycolysis already, my recorded lecture, you should be able to explain why we do this silly thing. Why undergo this reaction mechanism? Why do we put the carbonyl in carbon 2? Why does this reaction happen? Symmetry, even splitting. Everybody's right. There's logic behind this. By putting the carbonyl there, it makes this bond beta to carbonyl. It makes that that bond labile, and that way we can split it. So everybody is looks like everybody's on the right track, and it means that we end up with 2,3 carbon equivalents, and that those 2,3 carbon equivalents can then enter a single set of enzymes and then be converted into energy. Otherwise, we'd have to have one set of enzymes for the 2-carbon compound and another one set of enzymes for the 4-carbon compound. That would be ridiculous. So this is some beautiful symmetry that happens there that we've evolved, and it's present in almost all of life. Okay, not almost all of life. So there we go. So this last step, we just close the ring. And let me draw this in a less ugly format. So go like that. And then these guys can go and pick up the proton, and you've closed the ring, and there we go, glucose 6-phosphate. Is that beautiful? So everything that, all the little basic lessons that we learned about chemistry here have just come to apply. We have our ketone tautomerization. We've got our acid-base reactions happening quickly, and our beta-carbonyl is dictating the reactivity. Let's move right along here to the next mechanism. So in this particular case, we got phosphofructokinase, PFK. So PFK is one of the most important enzymes in glycolysis. It's the main regulatory point. It's a major choke point that dictates flux, and so we're going to be learning about more about that in our later lectures. But let's talk about it in terms of chemistry. You know, what this reaction is taking this molecule here, and you're ultimately making this molecule here. We're getting it ready so that we can split it, split this molecule in half right there, right? So why do we put a phosphate on in the carbon 1? What's the goal of that? It looks like Robin's already on it, or if that was, it may have been an answer to the earlier one. Yeah, she's right. That's exactly right. It's symmetry. We're putting the phosphate on so that the molecule will be symmetric when we're done. So how does this reaction occur? Tell me, what's the first step of this reaction? Oxygen attacks the phosphate. That's exactly right. So the chat was correct. We have this. And again, I'm just going to simplify this. So now I'm no longer going to show you the intermediate steps of the additional elimination, but everybody should now know that this is a 2-step reaction, not a substitution reaction. And then you have an ADP leaving. Does that make sense to everybody? I will, okay. So the cool thing about this is that we've gone from first principles, where we just learned that, we learned a few categories of reactions. I showed you a structure, and you were able to predict how the reaction occurs and what product it makes. That's really cool, because now glycolysis isn't about memorizing the structures. It's about knowing the logic, the chemical logic that gets you from one structure to another. And when you know that logic, it applies to all of the reactions you're going to learn about. It applies to all biochemistry. So this is some of the hidden beauty in biochemistry that I love. Is that not everything is happening randomly. These structures are all occurring for a purpose. Okay. So aldolase, so we already did this one last class, so we'll do this one quickly. What's the first overall thing that needs to happen before this chemistry can occur? Ultimately, we're going to be splitting this bond, but in order to split that bond, we've got to do what? Yep, we've got to do the ring opening. And why do we have to do the ring opening? Everybody's right. We do need to do the ring opening. What's the logic? Why do ring opening? We have many options here to make a carbon nucleophilic, and that's the answer that I was looking for there in the chat. Is exactly right, because currently, if we want to do the split, we're going to have to make something as beta to carbonyl. The beta to carbonyl is what makes that bond labile, and without opening the ring, it's not beta to carbonyl, so it's not reactive, right? So, we got to do that, and so this ring opening reaction, now you guys should recall, it looks just like this. And then these guys go out, pick up a proton. This is the same as before. And now we have our nicely open structure. And this this reaction should look familiar to you. Which bond is breaking? I'll give you an option. 1, 2, 3, 4, 5, 6. Chat, which one's breaking? Bond 3, everybody's correct. And why? Why is it breaking there? This is beta carbonyl, everybody's right. So how does that reaction occur? It occurs just as we have learned it. And like that. Woohoo! Bonds beta to carbonyl are labile, and then we get this nice form. This is glyceraldehyde 3-phosphate. Yeah, glyceraldehyde 3-phosphate. And then we get this other molecule that this funky little intermediate form. So what is this molecule right here? Dihab, everybody's right. So the molecule I just indicated there is dihab, dihydroxyacetone phosphate. So what is this thing? Nope. That is nope, is neither. It looks a little bit like PEP. It is not that. It's not glyceraldehyde 3-phosphate either. It is the ketyl form of dihydroxyacetone phosphate. Remember, good. Yes, Robin's right. Exactly. So it is actually dihydroxyacetone phosphate in its ketyl form. In order to get it from its keto form over here to this other form, which you guys remember, you have to go through ketoenol tautomerization. And so how does that occur? What is the step that needs to take it from one form to the other? Tell me, what needs to happen?
There's one question. So the only rationale I don't get in all these mechanisms is how do we determine which hydrogen is extracted by the base in the first step?
Well, so the question is, how do we figure out the reactive base? So there are a couple answers to that. Most of the time, it's the one that that's beta carbonyl is the one that we're working with, or it's the one that gets us to the structure that allows us to do things. If we were to if we were to abstract any other proton from here, we wouldn't get an open ring, right? We would get a very lonely negatively charged oxygen. And so, if we want to move from here to here, there's only one proton that's possible to abstract to get you to dihab. Which one is it? I will give you some options. Options are, let's see, 1, 2, 3, 4. Yep, 2. Chad is right. So let's abstract number 2, ketoenol tautomerization. We'll abstract the base from number 2, and whoop, that goes out to a proton, and then you get this form right here. This was in the quiz set. This is not a redox reaction. These two things have the exact same formulas. Either one is oxidized or reduced because they have the same number of electrons in both cases. You have to lose electrons or gain electrons for it to be redox. Is everybody comfortable with that? Yes, yes, yes. Moving on to the next one. So we already talked about this a bit in class here, so I'll go over this quickly. The reaction, as I showed you here before, this is perfectly correct. You can show the reaction this way. this is how it would occur without an enzyme. These reactions are happening in biochemistry. They're catalyzed and controlled so that we can control the rates and we can improve how quickly they go. So the enzymes lower the activation energy barrier, so the reactions proceed more quickly. And part of the way they dictate chemistry here is that they use the enzyme to catalyze the conversion. And so this is what we talked about in our last live stream, that lysine is actually, catalytic lysine is actually used in the actual mechanism that's used in the enzyme. But the chemistry largely proceeds the same way that we showed it before, with the base abstracting these guys. Whoops. Yeah, and then this going out to proton, that's ultimately leaving this guy here coming out. And we got to get down to our next form here. Oops. Right. Oops. I'm doing the catalytic version of it, sorry. So sorry guys, just doing the non-enzyme catalyzed version of it here. So we get attack of the nitrogen there on the hydroxyl that's forming this amine bond there, and then ultimately this guy comes off, picks up a proton, and you form the shift base here that you should recognize from our last class. How do we move from there? I'm just going to move quickly through this guy because I know we've already done this there. This guy is breaking here, and the reason it's breaking there is that this guy is beta. That bond right here is beta to a pseudo-carbonyl, right? This shift base acts as kind of a pseudo-carbonyl that allows this glyceraldehyde 3-phosphate to leave, and then we have this dihydroxyacetone-like structure attached to the lysine. Well, in order to regenerate the enzyme, we have to kind of reverse the reaction series that we just went to. So that goes to this form right here. So we've regenerated our shift base in the intermediate right here. And then this reaction just proceeds exactly in the reverse direction from what we just saw a second ago, where it picks up the proton. You go through this intermediate form right here, and then a base abstracts this hydroxyl, ultimately allowing this amine to exit, and you're getting your dihydroxyacetone phosphate right there. Does that make sense?
So is it essentially a hemiketal reaction?
Hemiketal reaction. I remember that word from 2 decades ago when I took organic chemistry. Hemiacetal. Yeah, I kind of vaguely recall those words, but I don't. I'll have to get back to you on that. Okay. So now let's get back to our where we are in the flow of logic. So we've got our molecule glyceraldehyde 3-phosphate. Now this guy was made from our aldolase reaction, and we have this annoying other molecule that is not symmetric, right? So what do we have to do? Is that we have to convert that dihydroxyacetone phosphate into a molecule that is symmetrical, so that you can use the same set of enzymes. If you don't do that, then the whole rationale for making the 3-carbon thing doesn't work, because you need 2 sets of enzymes. So why do we have triphosphate isomerase? So that we have 2 units of glyceraldehyde 3-phosphate. All right, so how does this reaction occur? So anyone want to take a guess?
Where does the previous reaction fit into glycolysis?
That is aldolase. This is the actual mechanism that happens in aldolates in the enzyme. So the chat in the question, or this is the actual reaction mechanism of aldolase when it's catalyzed by the enzyme. Yeah. So all right, back to this question. What needs to happen? We have people are saying a base abstracts a proton. Okay, which proton? we have options 1, 2, 3, 4. Okay, we have many, many people saying 2. Okay, 2 or 4. Yes, all of you people are right, 2 or 4. The correct answer is 2 or 4, but the most correct answer is 4 because it would be impossible to draw it otherwise because I'd have to work entirely back up here. So let's do number 4. So the base subtracts this proton here, and that goes to there. These guys go out to there. Good. And then you go to this guy here. What's this type of conversion called? What is this? Tautomerization. That's right, ketoenol tautomerization. So then the base subtracts the proton there. And what happens? Ta-da! Cool, huh? Looks familiar? So we now have glyceraldehyde 3-phosphate. We have 2 units of it. So moving on, GAPDH. So I hope for some of you are getting a tingling of excitement here, which is that we have just learned a handful of reactions, and now we've gone through all the priming phase of glycolysis, and every reaction mechanism that we've gone through follows the same set of rules. It doesn't look too scary anymore, does it? So let's see if that continues here with GAPDH. So as you guys know, GAPDH is a really important enzyme here for glycolysis, in that it's performing this essential function of substrate level phosphorylation. And that's what the payoff phase of glycolysis works.
Why is TPI deficiency lethal?
So why is TPI deficiency lethal? Why would you think? Class, why would be a deficiency for one of the enzymes in glycolysis be lethal? Ideas from the class? Well, if you don't have it, you're not going to be efficiently converting your glucose into glyceraldehyde 3-phosphate. This is kind of an aside question, but like if you have a fructose 6-phosphate and you convert it into dihap plus glyceraldehyde phosphate, and this molecule here converts it, or the triose phosphate isomerase converts it from dihap into GAP. Well, as you probably recall, all these reactions are reversible, readily reversible. They're happening at equilibrium. And so if this reaction stops, like, so you have this plus this, what happens is you get a big buildup in concentration of this molecule, right? So the net direction of the reaction goes that way, right? So if the aldolase reaction stops because you're building up the product, then you don't make any ATP and you die. Does that make sense to whoever asked that? Yeah. Yes. Okay, let's move along.
Oh, another question. Is there 2 molecules of GAPDH?
Every time aldolase is produced, after triose phosphate isomerase, it produces a net of 2 glyceraldehyde 3-phosphate. But that's after the triose phosphate isomerase reaction, right? So aldolase, takes FBP and makes dihap plus GAP, and then triose phosphate isomerase makes dihap into GAP, and that goes down to the rest of glycolysis. Right? Okay. Back to reaction mechanisms. So This is glyceraldehyde 3-phosphate dehydrogenase. This is the one that allows us to do our phosphate level or substrate level phosphorylation step. And so this guy here starts off with, there's a catalytic sulfhydro group on cysteine inside the enzyme. And so what that does is, whoops, I've got to turn that into, it undergoes a nucleophilic attack on this aldehyde here, on the glyceraldehyde, which picks up a proton. And that results in this intermediate right here. Okay, now we have to abstract a hydride. So quick question, which is a hydride? I'm going to give you some examples. Which of these is a hydride? A, B, or C? Yeah, see, everybody's right. And is a hydride an acid, a base, or something else? Taric is the right one. Almost, yes, it is a reducing agent. It is not an acid or a base. When you have a hydrogen with two electrons on it, it is a reducing agent. That means this is a redox reaction. Sneaky, he's right. So this is a reducing agent. This will do some wild chemistry when we come off. And so how does this work? That means that we need to be making we need to convert NAD to NADH, right? NADH. That is a redox step, as you guys recall. So what needs to come out of this molecule here, this intermediate? What needs to come out of it in order to make an NADH? A hydride, correct. Very good. So in order to complete this reaction, we have to have a hydride come out. And where is the hydride? I will give you options here. We have 1, 2, 3, 4, or somewhere else. Okay, other ideas? Yes, we have a split opinion in the course, but is indeed number 3 is the place that we need. This is the site where that hydride will leave. So how do we get the hydride to leave? How do we make it reactive? Do you think it'll come off directly? Yeah, so Cameron is right. So the way we get this to catalyze it is we actually use a base to abstract the proton right there. And those guys go right to NAD. Is that cool? I don't see loads of stoke. Come on, guys, this is amazing. We're making gas. Very good. Stoke, this is sick, yes. So the cool thing here is then you get your NADH, and then you end up with this guy here. What's the problem? Why doesn't the reaction end there? 2 problems. Tell me the 2 problems with that reactant. Yeah, it needs to regenerate the enzyme. That's absolutely right. What's the other problem with this thing? We've made an NADH. Have we made any progress towards making an ATP? No, right? Isn't the end objective to remake our ATP that we've committed into this? So this is the neat thing about this, is that this inorganic phosphate, so this is kind of unusual. Phosphate doesn't, in the reactions that we've been learning, very rarely the oxygen is acting as the nucleophile, but this is one exception. So we have one here and one elsewhere where the oxygen on the phosphate is acting as the nucleophile. And in this particular case, we have, this guy coming off, picking up a proton, and then you have regenerated your sulfhydro group here. And you have made this glyceraldehyde 1,3-bisphosphate. Pretty cool, huh? So this is very this is the underlying beautiful chemistry that allows life to work. If it weren't for this one reaction, there would be no life because we wouldn't be able to regenerate ATP that we committed into glycolysis. So this little trick here is super amazing. It has a problem though. In order to make all this work, we had to do this redox step right here. And so keep that in mind, because later on, we're going to be talking about this. If there's no oxidized nucleotide, if there's no NAD, this reaction can't work, okay? No NAD equals dead. So let's move along. Glyceraldehyde 3-phosphate dehydrogenase. Oh, sorry. Phosphoglycerate kinase reaction. So this guy is making a is going to be making our first payoff reaction here, and this should be fairly intuitive. But tell me, guys, what's going on? How do you make an ATP this way? What happens? What's the first step? How do you make your ATP? As everybody will probably remember, ATP is coming off here. Yep. So we need to somehow add this to this. And how is that going to work? What attacks what? Probably an oxygen is attacking a phosphate. Yep. Okay. So let me give you two options. I've got option blue, or I've got option purple. So is it 2 or 1? 1. Everybody's right. Blue. Blue is the new red. And so you guys are right. The phosphate's attacking here. For those of you who don't see why, that's because you don't generate this free molecule the other way. The other way would make you would give you a diphosphated thing. So this is 3-phosphoglycerate. What does glycerate mean? That means this structure. It's got the carbonyl on it. So this is very cleverly named glycerate, 3-phosphoglycerate, because it's got that carboxylic acid on the end. Woo! We're almost through. We're charging through glycolysis. We're getting here to the next reaction. Stoke should be very high because this is getting us one step away from the big, mighty payout reaction, the phosphenolpyruvate reaction. Stoke is off the charts. The Stoke meter's pegged. Good. So how do we move on from here? Well, we need to move that that phosphate from the 3 position to the 2 position, because the 2 position is ultimately where we were going to make our double bond there for our phosphoenolpyruvate, and we're going to make the ene. So we got to move the phosphate to the correct position for making the ene in the next reaction. So how the heck are we going to do that? Well, it's currently in the wrong position, and as it turns out, you can't isomerize from the 1 to the 2 position directly. There's nothing like a keto-enol tautomerization that'll move it from one position to the other. And so the life has a different chemistry. It's called a mutase reaction. This is not an isomerization reaction in the classical sense, in that it is not the molecule just rearranging itself. The phosphate actually has to come off and be reattached. And when you do that, that's what a mutase reaction is. So let's see. All right, how do you guys think this works? What gets you from this point to this point? Tell me, what happens? What happens? Hydroxyl. Yes, good. So which hydroxyl? Is it somewhere on this molecule or this molecule? 1 or 2? 2, bottom. Good. Everybody's got it. We only have 1 hydroxyl there, so that makes it pretty obvious. And that means we get this guy, right? And the nitrogen goes there, and that makes this free side chain. Okay, what is this, by the way? Histidine. Oh, good. The class is very good. That's a histidine. Very good. I'm so enthusiastic to see you guys know that already. That is a histidine. It does acid-base chemistry. It also adds, in this particular reaction, it adds as the substrate for the phosphate. But it's a very frequent participant in the active site of enzymes. Okay, so that catalytic histidine has donated a phosphate. And then what's the next step? do you think? The histidine turns around and acts as its own nucleophile. So some of you are like, what the heck is going on? Why would it do that? It's then just remaking the same molecule we just had, isn't it? It is on this guy, except the difference is now now it can be added to a different position, right? That guy comes out, and there we go. We have our final product, the mutase. Does that make sense, everybody? So it came in with a phosphate right here, and there was a phosphate in the enzyme, right? And the first step is we added a new phosphate, ended up with this 2-phosphate weird molecule intermediate. And the last step is the original phosphate that came in gets donated back onto the histidine. Make sense? Phosphate trading cards, absolutely. This is Magic the Gathering biochemistry style.
So question.
Yeah.
How is the phosphate removed from histidine at the end?
It's not. The question is, how is phosphate removed from histidine at the end? And the answer is it's not. It was there to start, and it was there at the end, which means it regenerated itself. And as those of you who have had your 393 will probably recall, if it comes in and it leaves in the same form, it's an enzyme, right? Yep. Okay, enolase. Okay, the stoke is now approaching uncontainable levels because we're making phosphoenol pyruvate. So you guys ready? Here we go, here we go, here we go. One more question. Okay, we'll take one more question. What is it?
Why does the inorganic phosphate grab a hydrogen when it's leaving, since it's not on the final product with the histidine, phosphorylated histidine product?
Yeah, so somebody is asking you there, remind me about the first rule of, what was the first rule that we had? So this is step 1, and then step 2 is, actually what I'm showing here is the proton here is going, this proton here that we're talking about, that's the question. Yes, everybody's right. Acid-base reactions happen quickly, but that's that proton right there. It is right there, right? And when it comes to acid-base reactions, they happen fast, and this is all happening in water. So adding and eliminating protons in solution is a non-trivial issue in biochemistry. Is that sort of answer? Good. It sounds like everybody's on track. Okay, finally, can I do enolase? I want to do it. Enolase. All right, everybody ready? Ready? Go, 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 go. Enolase is so cool because we're going to make this guy, and this molecule, as you know, is very close, very, very close to our end product here, which is this guy. What is this molecule here? What is it? Pyruvate. Yeah, this guy right here is pyruvate. And this guy here is phosphoenol pyruvate, PEP. Right? We know that this is the endpoint of glycolysis. So all we have to do is figure out a molecule that's going to get us there and make that. And this phosphoenol pyruvate, this is such a cool molecule, PEP. It is a super high energy molecule. It is very unhappy. And it is what allows us to prep and get ready for this final step that makes that gets us to the final payoff reaction. So how do we get here from this molecule right here, which is 2-phosphoglycerate? How do we get from there into our enol form? Tell me what needs to happen first. Does this look familiar, this and this? You should be able to look at that and tell me, how are those two molecules related? moving a double bond. They're not really resonance. This is something special. We call it, what is this kind of functional group called? Yeah, right, we got it, tautomerization. Yeah, ketoenol tautomerization. We saw that we were starting here with a fully saturated group, and then we ended up with the ketone. So, hey, look, sounds like it's working. So we need to abstract a proton. What do you think the most acidic proton would be? Would it be 1, 2, or 3? 3, everybody's right. Why 3? Why is 3 the most acidic? Beta carbonyl, look, learning has occurred. B. So that guy goes there. These guys go here. These guys go there, and we end up with this beautiful enol form of it. So in an enzyme, do you ever wonder why magnesium, like that's on the packages of cereal, they find out magnesium concentrations? It does this in biochemistry. It helps coordinate these carboxylic acids. That's one of its functions. And so it sits there in the enzyme and it helps stabilize this is a divalent cation, is what they call that. And it stabilizes these two negative charges on the enol form. Okay, and then we need to move the double bond from here to here. So how the heck does that happen?
Oh, a couple of questions.
Yes.
So, how is this a favorable reaction?
How is this a favorable reaction? It gets us to the final product. It's, I mean, these guys, the tautomerization is it's not terribly uphill. Like this is it's somewhat sterically hindered because you have these two guys on the same side, and you are going kind of uphill when it comes to heat of formation. But if you have a tiny amount of product and a lot of substrate, you can drive it that direction. That's what happens in biochemistry. Okay, so how do we get from here to here? The answer is, or I'm sorry, no, not from there to there. We're moving on the next step. How do we get on from the ketone from the double bond to here to the double bond there? What do people think?
Another question is, what is the carbonyl grabbing hydride?
Oh, here?
Yeah, I think.
That's a proton.
How does the carbonyl grab a proton here?
Okay. Well, we're in the way where we're drawing it is, I don't know what you mean by how does it grab a proton? And it's an acid-base reaction, right? What's the concern? Sure. Yeah, sure. I mean, I think the question is, why was there a proton there and not? Why was there showing a proton here and not there? Why? Because acid-base reaction. Normally you show these reactions as being catalyzed by a proton, right? So I guess in this particular instance, we have a magnesium that's sitting here. That's pulling some of that. Electronegativity over there and stabilizing it. Does that make you happier? Yes. Okay. Okay. So how do we move from here to here? We're going to have to be quick. We only have 2 minutes left, so I'm going to have to shut down the chat here for a second so we can show. But this guy goes right there. And then what's the issue? This guy has to go and pick up another proton. Look, then we have our water leaving and we got our ketone form. Yes, 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 yes. We're almost there. We're almost there. Finally, we're going to do our last step here. Pyruvate kinase reaction. Okay, so we're going to finally make our pyruvate, which is very exciting. And we've got to make an ATP out of this, right? So what attacks what? What attacks what? What's the nucleophile? Yep, this is another case, weird case where the where the oxygen is attacking the phosphate, and that forms this guy here. Whoop. Yep, and that ultimately makes this beautiful molecule right here, which, as you guys all know, is our friend's pyruvate. Yay! That's so cool. We've gotten through glycolysis, all the mechanisms there. Of course, normally we have this issue that you have to remake your NAD, because if you don't have NAD, as we said at the very beginning, you're dead. And so the way, if you don't have an oxidative phosphorylation, you want to regenerate your oxidized nucleotide, you got to get rid of it, right? So this last step, how this happens is that you can take your NAD, form there, and this hydride can then go and attack this guy to form that. Is that beautiful? I'm going to make this hydride there, ends up being that molecule. And then you've got your regenerated form. Ta-da! This is why you make lactic acid when you run really fast, is because you need to regenerate NAD to make ATP when you can't get oxygen into your tissues fast enough. The reason why is because you need an oxidized nucleotide to make it happen. And that is yeah, so that's the whole premise of the cycle. Okay, we're running out of time today for today's class. I will post this up online, both with the structures that you see with the skeleton, but also with the arrows drawn. I encourage you to go through each of the steps, do this for yourself, and if you have questions, let us know. This is pretty cool, and after you know this, we're going to do the TCA cycle, and you should be able to predict each of those reactions from scratch if I just give you the structures. Thanks, guys. Stoke is high.